My name is Anke and this is my colleague Tim. Tim and I, we've had the privilege of leading NeuroTech Leuven this year. We are beyond excited to share our progress with you today.
The Mindwitcher allows us to play The Witcher free in a rather unconventional way. Next to your usual keyboard or controller, people can navigate the world using their brain. We have two different input signals that we use for this. One is related to physical or imaginary movement, and the other signifies your emotions.
But beyond the game, our code is also available for researchers that want to develop new applications for paralyzed patients to really remote control things with their brain signals, with their EEG. So now, let's dive into the code and the work our team has accomplished.
For this project, we chose the award-winning game The Witcher 3. First of all, we chose it for its great developer support. They allow us to modify the game without doing any additional installs. Secondly, we chose it for its great magical system. The player, Geralt of Rivia, has the ability to cast magic spells, which in our project can be controlled by the brain, which means you're truly doing a magical thing.
Yes, and these brain actions are used as an extension of your way of playing the game. We use imaginary movement brain data to simulate virtual keyboard presses through the game, and we chose this way of interacting with the game because it's very simple and also extendable to other games. Then we can also control the weather through looking at your emotions, and that way your mood is truly reflected into the game.
To collect EEG signals, we use a professional headset provided to us by NeuroTech. As you can see, it has 8 channels in it. We gather the signals using a flexible cap, and then we transfer the signal to an amplifier using a cable. While our users immerse themselves in the Witcher experience, we collect 2 sources of signals. One that originates from the motor cortex, and the other one that reflects the emotional state of the user.
Before we dive into the technical details, I want to discuss imagined movement. Imagined movement is when you mentally simulate actions without physically moving. It's a fascinating area with great potential for applications like brain-computer interfaces. However, it's challenging because not everyone can easily perform imagined movements, and it requires training. For our initial project, this was out of scope given the limited time. That's why we are currently focusing on real movements. These real movement classifications trigger actions in the game, such as performing a magic spell by raising your left arm or calling a horse by raising your right arm. The exciting part is that signals from real movements closely correlate with those from imagined movements. This means that in the future we can use techniques like transfer learning. This could greatly enhance our game by allowing imagined movements to trigger game actions as well.
Okay, as Tont and Lars already explained, for the imagined movement classification part, we're going to be using an Neuro headset. And the Neuro headset is an EEG system consisting of 8 channels, of which 2 are located directly above the motor cortex, and these channels or electrodes are called electrode C3 and C4. Now, whilst this system is going to capture brain waves, we're going to divide this signal into several windows, which are called epochs, and these have a length of 2 seconds worth of data. And we're also going to overlap them with 50% to have continuous classifications. And this means that every second we're going to take a 2-second window on which we're going to perform classification. An example of such a raw window of data for one electrode looks like this. And of course, as you can see, this contains some high frequency noise. So typically we want to do some more filtering and pre-processing steps to remove this. And this typically concerns or pertains to high frequency noise and power line interference noise. And in this case, we can remove both of those using only one filtering step, which is a bandpass filter with a cutoff frequency on the lower end of 0.5 Hz and a cutoff frequency on the higher end of 40 Hz. And an intermediate result looks like this. Already looks much better, no? So after this, we're going to do some common average referencing to remove any residual noise that is shared among all the electrodes. And after this, we have fully clean EEG data windows to perform classification on. Now, after this, these windows can be passed to our 2 classification model pipelines, one a machine learning, a classical machine learning pipeline, and the other a deep learning classifier. Now, next, Wout will tell something more about the machine learning pipeline.
Thank you, Matthias. To initially train and test the machine learning approach, a public dataset was used. This dataset, the VisionNet dataset, was recorded with a BCI 2000 headset containing 64 channels of EEG data. Those recordings consist of 109 subjects with multiple 1 or 2 minute trials per subject. These trials include 3 classes, one for left hand movement, one for right hand movement, and one rest state. As Matthias explained earlier, those trials are pre-processed and epoched to a complete set of around 10,000 epochs. In the machine learning pipeline, only the segments representing left and right are included for training the model. A subject-specific approach is adopted, implemented by applying a common spatial pattern or CSP filter customized to the unique brain signals of each individual player. This filter enhances the difference in variance between our 2 classes, which also decreases the large differences between subjects. From this new mixture of channels, the 2 most discriminative channels are extracted. Following the CSP filter, a set of features is extracted from those 2 most discriminative channels. The features are both based on the time domain and the frequency domain to obtain a maximal amount of information. With these features, a gradient-boosted classifier is trained and evaluated. In case of the VisionNet dataset with 64 channels, this approach allows a final F1 score of 84%. However, when the amount of channels is reduced to the 8 locations of the N-Euro headset, this performance unfortunately drops to around 68%. The fact that this pipeline contains a subject-specific component, the CSP filter, is both a blessing and a curse. On the one hand, it facilitates a rather simple implementation to achieve good results, but on the other hand, it does result in the requirement of calibration data for each new subject trying out the system. This calibration stage makes it less plug and play and usually requires a second person to assist in this process. Nevertheless, this model performs quite well and can be stable even with smaller amount of data available. With some further improvements of the model in the 8-channel setup, this approach could make a Mindwitcher out of everyone.
Okay, just as is the case for the machine learning pipeline, as explained by Wout, we are also going to pre-train our deep learning models using a public dataset, namely the VisionNet dataset. This is namely necessary because deep learning models are inherently data hungry. To perform the deep learning based imagined movement classification task, we chose to use a transformer, which is typically a deep learning model consisting of multiple modules. The first module typically consists of convolutional layers, which encompass both temporal filters, but also encompass both spatial filters. Now, the results, the feature maps from these filtering layers, are then passed to an attention mechanism as displayed here, which seems quite complex, but actually just forms a proxy to autocorrelation. The output of those layers are then transferred to a fully connected set of layers, which then performs the actual classification, returning the probabilities for each class for a given input sample. Now, using this public data set, which as Wout already explained, was obtained through a 64-channel headset, we obtain for a new unseen test subject an F1 score, which is pretty good, namely 80%. Unfortunately, not every headset has this amount of channels. For example, the Neuro headset has only 8 channels. Because of that, we will need to fine-tune our pre-trained model by unfreezing the first and last layers to get better at a classification task in a situation where only 8 channels can be used. Unfortunately though, when we do this fine-tuning, the performance drops for a new unseen subject to an F1 score of 62%. Now, multiple reasons are possible for this, and mostly related to the data hunger of deep learning models, with the first reason being that it might be possible that 8 channels simply isn't really enough to have enough information fed to a model to make an intricate classification task like the imagined movement classification task as is performed here. Another option is simply that we did not collect enough data to do this fine-tuning, leading to an unresolved amount of fine-tuning and fitting of the model, leading to a poor generalization to new test subjects for the new hardware. Nonetheless, the advantages of deep learning also become clear, namely that it is subject independent compared to the machine learning pipeline. And this also means that in practice, it is more plug and play. You just put the headset on the person and you insert the model, et voila, you're good to go.
Besides imaging movement, we can also pick up emotions by using EEG signal. These emotions are then categorized into 4 different categories: happy, sad, fear, and neutral. These categorized emotions are then later used to directly influence the environment and the weather conditions of the Witcher game. If the user is happy, the weather condition and the environment will be vibrant and sunny, for example. Our model is trained on seed4 dataset. The dataset was created by showing user or the subjects a movie clip and then recording the brain signal. There is no objective ground truth in emotions. We are aware of the fact that categorization of the emotions is influenced by factors such as culture, age group, geopolitics, etc.
The storm, damn it.
We have been able to decode these emotions through a powerful tool of machine learning. By using the seed4 dataset provided by the BCMI laboratory, we have had access to some groundbreaking EEG data recordings throughout 15 users, with each containing 3 sessions with 24 trials. Each of these trials has either a happy, sad, fearful, or neutral clip. Our pipeline works as follows. We first trim the edges of the signal in order to remove any artifacts that are unnecessary. Then we segment the data into 4-second clips with a 50% overlap to then further feed it onto a bandpass filter that improves the signal quality and clarity. Now comes the heart of the process, which is the feature extraction. We have analyzed the EEG data across 8 different channels as well as 5 different frequency bands. By then computing the power spectral density as well as the differential entropy, we have obtained a structured data frame per segment containing 80 different features. Further on, we use a gradient boosting classifier with grid search in order to train our model to be able to detect the emotions encoded within the EEG data. Further on, we use a pre-trained model with the NeuroTech real-time EEG data in order to predict the user's emotions. In this current model, we have obtained a 66% accuracy due to the fact that we have only 8 channels and some of those channels' data is not necessarily useful to classify emotions. However, if more channels were to be included, such as the use of 64-channel headset, we could further improve this accuracy.
One of the most important and challenging parts of our project was to ensure smooth integration and communication between our hardware and software components. Using OpenVibe and Python, we've constructed 2 robust pipelines that seamlessly allow new players to become a Mindwitcher in no time. The OpenVibe acquisition server connects to the EEG headset, streaming directly to the acquisition client in OpenVibe. Then, depending on the specific model that will be used, either the machine learning or the deep learning pipeline processes this data to facilitate actions in the game. For machine learning, this consists of 3 steps. First, collecting data. Second, calibrating or retraining the CSP filters. And third, playing the game. As Matthijs has explained before, deep learning is more plug and play, and thus allowing the user to directly play the game from the start. In order to ensure a smooth user experience, these steps can be run automatically and sequentially from one controlling Python script.
Beyond the confines of our lab, the outreach team made meaningful connections with patients and healthcare professionals. Through conducting interviews, we were able to gain valuable insight concerning the further progression of our project and its real-world applicability. So now let's have a quick look at the highlights of those interviews.
Dus ja, ik ben Veerle. Ik ben een vrouw van 55 jaar. Ik ben in het leven eigenlijk opgeleid als logopediste. Werkzaam al bijna 28 jaar op het Centrum voor Genetica. Maar mijn leven wordt voor een groot stuk mee bepaald door het hebben van een progressieve spierziekte.
I'm Dr. De Maagd, a resident neurology, and currently also promovendus on ALS research in the UMC Utrecht, the ALS Center of the Netherlands.
What do you think is the potential of this kind of technology? Do you see any applications outside of the gaming world?
Brain to computer interface has a lot of potential, I think, for indeed you bypass communication that is currently done through eye movements, so that might be a lot faster for certain tasks or for certain things, instead of having to do everything with your eyes. What we use those VR for is to test cognition. And yeah, I think the more you use it, the more application will appear.
Lijkt mij het project zoals dat van jullie in een verre toekomst zal voor mij zelfs die handfunctie waarschijnlijk ook wegvallen. Dat weten we niet, maar die kans is zeer groot. En ja, lijkt het voor mij precies zelfs een optie in de verre toekomst misschien om dingen met mijn brein aan te sturen. En daar droom ik misschien toch nog wel een beetje van.
As we come at the end of our presentation, I want to thank our supervisors, our sponsors, but especially every member of the team who has made this project come to life.
From pre-processing EEG data to developing cutting-edge pipelines, modding the game and putting it all together, our team has shown incredible dedication and expertise along the way.
But of course, the journey doesn't end here. We're going to continue to develop the Mindwitcher, we're going to enhance it, and we look forward to seeing you next year. Thank you for watching.